Okay, welcome back, everyone. This will be our final class, final lecture of the fall 2020 semester. But I guess it's actually 2021 now. But all right, so what we will be doing today is we will finish up our discussion on recursion, and then we will spend some time also going over a final exam review so you guys can know what to expect in the upcoming final exam. That's going to be Monday morning at 9:30. Let's see, a couple other things I wanted to make sure to say. Oh, again, you have that assignment 4 that's out. Its due date is officially the Sunday night before the final exam. I cannot accept late submissions on this. I need to make sure that I announce that again. Because of the situation with the final exam being the next day, it will not be possible to accept a late submission for that. But again, this assignment doesn't count towards your in the semester assignment grade. I'm going to use it as part of your final exam. Okay, so yeah. One other thing. And I guess I can go over this on the final exam too. Expect that there will be questions based on that assignment. So make sure you really understand what's going on in that assignment. And so just like we would normally have given you a quiz in a couple of days after the assignment was due to test your understanding of the assignment you had just done, in the same way, we will give some questions on the final exam related to the assignment to test your understanding of the assignment itself. Okay. So is there anything else I specifically wanted to mention? I should write these things down. So let's just go ahead and get into recursion. All right. So let me go ahead and let's see, share my recursion slide here. Okay. Actually, I want to move this over here. All right. Okay, so where did we leave off? Let's see. Let me move down. We did all the whole Fibonacci and the factorial. We did factorial. We did Fibonacci. We talked a little bit about why Fibonacci. We talked a little bit about this, where it's really, even though it seems most natural to do it as a recursive definition, since its definition is kind of recursively defined in terms of itself. But in actuality, in terms of efficiency, it's very, very inefficient to solve Fibonacci in programming using a recursive methodology. And the reason why is because of how many times you have to do the same work over and over again. So see here, Fibonacci of 2 is determined for the purpose of finding out what Fibonacci of 3 is. Like, we use Fibonacci of 2 plus Fibonacci of 1 to get Fibonacci of 3. But over here, we do it again. We go and recalculate the same information twice, right? So we shouldn't do the same calculation twice if it's not necessary. Okay, and you'll learn a lot more about this and about how to be more efficient with your algorithms in your algorithms course and your algorithms and data structures courses. But I do want you to at least kind of have that in your mind, that this course, what I want you to be able to do is I want you to be able to solve the problem correctly. Later, once you have been able to do that, later, what we're going to help you do is not only solve it correctly, but also solve it efficiently. And that's what your algorithms course is going to be all about. Okay, so anyway, so we're going to move on from Fibonacci. So we can think recursively for a lot of problems. Okay, Fibonacci, factorial, these are just some examples, but here's an example of where we could use a recursive definition for the is palindrome method. So you remember is palindrome, we pass it a string, and if the string is the same forward and backward, then it's a palindrome, right? Okay, so what we're going to do here is we're going to say, well, do you guys remember how we did that? Do you remember how we looped through comparing the first character in the string with the last character in the string. And then if they were the same, we moved in, right? And then if they were not the same, we just returned false, right? Because if the character at the end of the string and at the front of the string and the end of the string were the same, we might have a palindrome, right? We don't know for sure. We just know that we can move in and continue looking through the string. But if they're not the same, we know for sure not a palindrome. All right, so we did that what we called iteratively. Remember that word from last week, iteratively, where we looped through, right? Well, here what we're going to do is we're going to say, okay, you know what? Let's think about this recursively. Let's say, you know, if the two at the ends are the same, then we really need to just move in. Let's not necessarily loop in using these variables and these iterators and stuff. Let's just look at the substring, right? Okay, so what we're doing here is if the string length is less than or equal to 1, so in other words, if our string is 1 character or 0 characters, we could have an empty string. That's what we'll call our base case. We know for certain a 1 character string is a palindrome. We know for certain that a 0 character string is a palindrome. Those are definitely both the same forward and backward. So we return true in that situation. Otherwise, if for the string that we're passing, if the first character does not equal the last character, then we return false. Now this is, we'll consider this another base case. One base case, we have a 1 or 0 character string. The other base case is we have a string where the first and last character are not the same. Okay. But if they are the same, then here's our recursive call. Okay, where we take our isPalindrome method and we pass it the substring that starts at the second character and goes to the second to last character. Okay. So if we think about it, I'll insert a text box and show you what we would be passing over here like that. Okay. Let's say that we passed that string race car. Okay. Okay, so we're going to pass it race car. Not with a capital R. Okay. Is it less than or equal to 1? No. Is the first character not equal to the last character? R is not equal to R? Nope, that's false too. All right, so we move on. So then we call the isPalindrome method with the substring that consists of these characters. So now we pass this. Then we check these. Is it less than or equal to 1? Nope. Are the first and last characters different? No. All right, so then we pass it these. I hope you see where we're going. Okay. Is it less than or equal to 1? No. Is the first and last different? No. So now we pass it our substring, which is just this. Okay. And now we have reached the base case. All right. This is only 1 character, so we return true. So this returns true to this call. Well, this just returns whatever it gets. So then we return true, and then this returns true. Okay. So I hope that's clear about how this works. Notice the 3 parts we talked about. Make sure you understand the 3 parts that are necessary for a recursive algorithm. 1 is a base case, at least 1 base case. Now it can have more than 1. In this situation, we have 2 base cases. All right, so we have a base case. We have a recursive call where we call the method itself. And we have, remember the last part, this is the tricky one. The last part is this convergence, right? Where we are converging to the base case. All right. So we know that we are going to get to either one of these two situations. We're either going to get to a string where the first character is not the same as the last, or eventually by continuing paring down, continuing to strip off the first character and the last character and passing through what's left, eventually we will get down to a string that consists of one or fewer characters. Okay, so this is how this works. This is how this recursive definition for an is palindrome method would work. All right. Now there is an efficiency, not a time efficiency issue, but there is a space efficiency issue in this. So in the iterative approach to the is palindrome method, in the iterative approach, where we looped through comparing first and last, then second to last, and so forth, we only had one string object in memory. Okay. In the is palindrome recursively, every time we call is palindrome, remember the substring method creates a new string based on the existing string. It doesn't change the existing string. It creates a new string. So every time, so this is why I typed it out. This is why I wrote it out here 4 times, to show you that 4 different strings are created. All right. In a problem like this, with the computing power that we have these days, this is probably not going to be a major problem. This isn't going to take up a lot of space in your computer and in your program to run this. But for larger problems that might do something like this, it could create a huge problem with a lot of memory being taken up for things that aren't being used. Like when we get down to this point here, this string, we don't really need that in memory right now, but yet here it is. And so if we get down to a very low level after having a large string up top that got called maybe 100 or so times, hundreds or thousands of times, then what would happen is you'd have all these strings in memory, and it could cause some problems. Okay. All right. But this is not so much an example to say palindrome is done better recursively, because what I'm saying right now is that it's really not in terms of the way Java does things. More what I'm saying is think about how some of these problems might be able to be done recursively, and sometimes they can be done better recursively. All right. So here would be an example of how we could do that same is palindrome method recursively, but we have remember we overload this method, right? So we have 2 different definitions of the is palindrome method. But here, instead of creating a new string every time, we just pass the same string, S, we pass the same string to our method every time, so we don't create a new string, but we just say, look, okay, I want you to look at a low position and a high position, and if at some point high becomes less than or equal to low, so they're either pointing at the same thing, same character, or high is looking at one character less than low, right? Then that's our base case. That means we've looked through all the string and compared the first and last characters all the way through, right? And that would be returned true. Otherwise, if the character at the low position is not equal to the character at the high position, we return false. And then finally, if neither of these situations are met, then we say, okay, look at the next character. Okay, take the same string, look at the next character on the low end, the next character towards the middle on the high end, and run it again. Okay, so this looks a lot like the iterative approach, but just using a recursive call instead. But again, if we look at it at the different pieces here, we have a base case, we have a recursive call, we have convergence. We're always moving towards one or more of the base cases. Okay, We're always moving to, eventually, if we keep adding 1 to low and keep subtracting 1 from high, eventually high will be less than or equal to low. All right. Okay. I don't want to go through the sort or binary search. I do want to leave those as examples for you guys to look at. The big problem I want to look at today, the one I want to spend a bit of time on today, because it's a fun one for me. So there's an old problem called the Towers of Hanoi. Okay. And the idea is that there are n disks. There's some number of disks, and they're labeled 1, 2, 3, and so forth. Okay. Now, if we think of 1, 2, 3 as being the size of the disks, then no disk can be on top of a smaller disk. So we can't have 2 on top of 3. We can't have that. All right. All of the disks are placed, starting at the bottom in down to 1. All right. Initially placed on tower A, on one of the towers. We can only move 1 disk at a time, and it must be the top disk on the tower. So we can't move, we can't move 3 off of the tower, like disk 3 off of the tower, if 2 and 1 are still on top of it. Okay, we have to move, if 1 is the top and we want to move a disk off of there, it has to be 1. Okay, it has to be number 1. Okay. Let me, I pulled up a couple of images. What I like to do is when I teach this class in person, what I like to do is I like to bring this with me to class that day. All right, some of you have probably played with this as children, or you might know, you might have a little brother or a little sister that plays with this, or cousin or something. My children are too old. We don't have this toy in our house anymore, actually, but my children had this when they were younger. And it's this is basically what we're looking at in the Towers of Hanoi, is you have this small disk at the top, small ring at the top, and it goes down, and each ring below is slightly bigger, right? And I can't move, I couldn't move the green ring off of this tower, right, without moving the red, orange, and yellow off first, right? So imagine that we had this set of rings, right, and we had this set of rings, and we had 2 other towers, and the goal is to try to move all of the rings from one tower, from one post to another. But we can only move 1 ring at a time, and we can never have a bigger ring on top of a smaller ring. Okay, so we can't just move ring 1 over. We can't just take this top ring and move it over, and then take this smaller ring and move it over on top of ring 1, and take this one and move it over again. Can't do that. We also can't take all 5 rings from the blue up. We can't just take all 5 rings, grab them all, pick them all up at once, and move them on over to the other tower. We have to move it 1 at a time. Okay. If you want to see an animated GIF or GIF, depending on how you pronounce it, of this is not it. This is it. Hey, I had this clicked up. There we go. All right. So this is from Wikipedia. All right. So this is kind of with a 6 ring. So this is how this would work, right? So we're moving this ring, right, all the different rings. I wish I could slow this down a little bit. All right, but this is how the problem works. So this is what we're trying to do. So as you might expect, since we are in the middle of a set of lecture slides on recursion, this has a very nice recursive solution, right? Okay, so again, this is a non-animated version of that same thing I just showed you, involving 3 disks. So here we want to move these 3 disks. Step 1 would be to move disk 1 off. Step 2 would be to move disk 2 over here. Step 3 would be, now we can't move disk 3. We can't move disk 3 yet, can we? We can't move disk 3 to top of 1 because that can't happen. We can't move disk 3 to top of 2. That can't happen. But we gotta move disk 3. So what we need to do? we need to make space for disk 3 by moving disk 1 over to this tower. Then we can move disk 3 over. Then we can move, now we need to get these two over here. We can't pick both of them up at once and put them over, right? We have to move disk 1 off first so that we can move disk 2, and then we can finally put disk 1 on top of the stack. All right. So if we think of it recursively, all right, then if what we're saying is we want to move n disks from tower A onto tower B, well, what if we think of it as 3 subproblems? What we really want to do, because what we really want to do is eventually we need to move disk N, whatever this largest disk at the bottom is. We need to move disk N from tower A to tower B, right? You guys understand that, I hope. What we need to get to eventually is taking disk N and move it from A to B. Right? But how do we do that? The only way we can move disk N is if all the other N-1 disks have already been moved off, right? So now what we need to do is we need to say, okay, our first problem is taking N-1 disks, moving them off of A, and where are we going to move them to? C. And the reason why we're saying C is because if we say the big problem we're trying to solve is moving the entire tower from A to B, then that means that we have to move disk N from A to B, and the only way to move disk N from A to B is if all the other disks are sitting over here at C. Okay, so first problem, move N-1 disks from A to C. All right. Problem 2, simple, move disk N from A to B. Now our final problem, move those N-1 disks from C to B. Okay, now it may be difficult. Some of you may be already seeing it, but some of you may be having a hard time still. I think I would if I were in your shoes. For some of you, might have a hard time understanding, wait, how is this recursive? Here's the thing. We just solved in 3 subproblems how to move N disks from A to B, right? Our 3 subproblems, move N-1 disks, move disk N, move N-1 disks, move disk N, move N-1 disks. But this problem right here is just a smaller version of the big problem we just solved, right? This problem right here is composed of move N-2 disks to B, move disk N-1 to C, move N-2 disks from B to C. Right? So you see how this problem is just a smaller version of this problem. Right? The N-1 disks is just a smaller version of the N disk problem. And that's really how we understand when we see something that looks recursive in nature. Okay, is that if a subproblem is just a smaller version of the problem we're trying to solve, that could be a recursive solution. Right? Okay. So the code for it here. All right. So we'll look at this in just a moment. Okay? But basically the idea is we have, how many disks are there? All right. We will move N disks, and then we have a from tower, a to tower, and an auxiliary tower. Now the auxiliary tower, that's important because we're going to pass that to our recursive call. Okay. So here our move disks is going to be our recursive solution. So if n equals 1, if we have one disk, stop. We're just going to move a disk, whatever, move disk, whatever, from tower whatever to tower whatever. Okay. Otherwise, if we have more than one disks, we're going to first move n minus 1. So if we have two disks, we're going to first move one disk from our from tower. Remember, all the ones that we're dealing with are on the from tower. Instead of moving it to the to tower, though, we're going to move it to the auxiliary tower. Okay. And then we're going to move whatever disk we're looking at. So if we have two disks, first we're going to move one disk from tower A to tower C. Then we're going to move disk 2 from tower A to tower B. Then we're going to move n minus 1, one disk from the auxiliary tower we just put it on to the 2 tower we're trying to get to. From C to B. Okay. So I hope this is somewhat clear. What I can do is I'll pull it up. Let me see here. Let me go pull up this guy. The Towers of Hanoi. Java problem here. Okay. Let me make it a little bit bigger so you can see it better, I think. Okay, so this is the code we just gave. Okay. All right. Next, compile. There we go. All right. So now if we run this, okay, we're going to enter how many disks? Let's just enter one disk. All right. The moves are move disk 1 from A to B. We're done. All right. That makes sense. All right. Okay. What if we enter two disks? Okay. Now we're going to move disk 1 from A to C, 2 from A to B, and move disk 1 from C. All right. That makes sense. Okay. Let's do it using 4 disks and see what happens. Okay, so now notice that this whole section from here down to here, right, this represents us moving the top 3 disks from A to C. Notice that we first move disk 1, then we move disk 2, then we move disk 1 back on top of 2, then we move disk 3, then we did the thing in reverse. So then we move disk 1, 2, and then 1 again. And now we have the top 3 disks are on tower C, and disk 4 is on tower A. So then we take disk 4, move it from A to B, and then we just do all that again. So then we just all that in basically reverse, moving it from C to B. Right. So all of these steps, all of these moves represent that recursive call, that sub problem of moving 3 disks. And notice inside of this even, there was this recursive call, this moving these 2 disks, disk 1 and 2, from A to B. B was the auxiliary tower here because C was the tower we were trying to get those 3 disks to. Okay. All right. So I hope this is clear. I have one other thing I want to do on this Towers of Hanoi thing before we move on, before we end. So what I'll do is I'll go ahead and call the first break now, right? And then we'll come back from that break at 10:20, and I will continue on with one more fun thing, one thing I want to talk about related to the Towers of Hanoi. And then we'll finish up in the second hour with the final exam. Okay. All right. So take a break. I will see you in 10 minutes. And if you have any questions during the break, let me know.